These are the challenge questions from part 5, book number 2. So describe in radians the angles that do these things. Cos, of course, is 1 at 0, and then again it's 1 at 2 pi, and then 4 pi, and so on. If you need the conversion, here it is, and you just divide to find the other conversions. But anyway, that's not good enough to describe all angles with no actual bound to them. So we're going to write this as 2n pi, where n is some integer number. It's just every time you arrive at an even pi. Of course, remember, you can also do minus 2 pi and minus 4 pi, of course, but I think this will be good enough. Sine theta is minus 1. Well, that happens at 3 pi over 2, otherwise known as 270 degrees. And then you have to add another 2 pi, and then another 2 pi, and so on, or take away 2 pi every time. I decided to write this as this because I noticed these are all multiples of 4, take away 1, and then just leave the 2 on its own, put a pi on the end. I think that works as a way of doing that. And tan theta is undefined. That happens when cos theta is 0, which is a pi over, because it's obviously sine divided by cos. So that's going to be pi over 2, and then you add just pi every time because you add 180 every time for tan, so just add pi a bunch of times, and then these are just all the odd numbers. So I just wrote it like this. And I think that's good enough for the first question. We've got a sector, radius r, arc length l. Remember, if that's theta here in radians, l is just r theta, and the area is r squared theta over 2. Rearrange this to say theta is l over r, and then you can just replace that in here to get r squared l over 2r, cancel the r's, and you get rl over 2 as an area formula. This one here says write an expression for CD in terms of AC and theta. Well, CD is just the arc length, which we already said was just r theta, so that's just AC times theta. Given theta is really small, such that AC is basically the same as AD, well, it is always the same as AD, because that's just the radius of the sector. But so small that's basically also the same as AB, and CD, which is this curve, is basically the same as BC. Deduce sine theta equals 0 is approximately theta, and tan theta are the same. So looking at this right angle triangle here, sine of theta is BC over AB. But if theta is really small, then it just says here that BC can be written as CD, and AB can be written maybe as AC. But CD over AC is just theta, according to this formula here. So sine theta equals about theta. And likewise for tan theta, that's AC over AB, sorry. Sorry, no, it's not. It's opposite over adjacent. It's BC over AC. I was doing cos. Not sure why I'm doing that. Of course, again, if theta is really, really small, AC can be approximated as AC, because that's actually what I want to use here. It's BC that I want to approximate as CD, and then CD over AC likewise is theta. And so we have those two things there. Next, it wants us to do something clever to show that cos theta can be written like this in the small angle things. So this is 1 minus x to the power of half. Follow this formula here, so it's 1 plus a half x, but x is going to be minus a half x squared every time we see it. The next one is a half times a half minus 1 over 2 times minus x squared all squared, which I've written there, and that's all we need here, so I'll just put in a character and get this. Now, how are we going to get cos this in any way? Well, look at this 1 minus x squared, right? That should ring some bells. 1 minus sine squared is cos squared. So if I replace x with sine of x, I think what I'm going to get is 1 minus sine squared of theta. Sorry, replace x with sine of theta, maybe, if there's a theta here, of course, is equal to this. So just replacing these with sine thetas as well. Now, 1 minus sine squared theta is cos squared, so the power half is just cos, which is super useful. And over here, sine squared theta, assuming that sine theta is about equal to theta, I think I can say sine squared theta is about equal to theta squared, because this is just sine theta times sine theta. Each one can be approximated as theta. That makes theta squared. Now, sine to the 4, if theta is really small, is going to be theta to the 4, but that's basically just 0. So I'm going to ignore that. And I'm just going to say this is my angle approximation there. I think that's good enough to go. Let's solve these for small angles. Again, these are the small angle formulas, just in case we need them, which we do, just in case though we actually need to write them down. Sine theta is theta, tan theta is theta, so this makes 9 theta squared plus 25 theta equals 6. Take the 6 over, factorize, and you get theta is this or that. But remember, these approximations only worked in the first place if theta is really small, which isn't that. So let's just say that it does work for this, I guess, and that's the solution. Next one, this is just theta. This is, be a bit careful here, this is 1 minus 4 theta all squared over 2. So just replace that theta with a 4 theta there. That makes 16 theta squared over 2 is 8 theta squared, times 5 is 40 of them. Move it over. I think that factorizes as well, and then you get two answers which are very close to 0. And so I think I'll accept both of those as solutions. And the last one, this just replaces with 4 theta. That replaces with minus 2 squared theta all squared over 2. Expand out and do some stuff and move over. And this doesn't actually have any solutions, I think, because b squared minus 4ac is less than 0. And so there are just no solutions to that one at all, I don't think. I think that's the whole chapter, and thanks for watching.